Hello everybody, welcome to the flipped homework for tonight. It's going to be numbers 3 and 4 on pages 50 and 51 of your workbooks. And this is actually going to be a really cool example because, as you notice, possibly if you've read ahead into this example, the data is going to be different than what we've worked with before. So let's get right into number 3. It says, Kara and Maria decided to spend one morning helping out a car wash to benefit a club that their grandparents have participated in for years. The car wash was a busy place. At the beginning, there weren't any cars, but between 9 a.m. and 10 a.m., the class washed 5 cars. From 10 to 11 a.m., the class washed 10 cars. From 11 to 12, the class washed 15 cars, and from 12 to 1, the class washed 20 cars. Maria kept track of the cars washed each hour. And here we have a list of the data. So in hour 1, 5, hour 2, 10 cars, and hour 3, 15, and lastly, hour 4, 20. So we have a list of data that came from the real-world question. It says, how would I write the domain and range for this scenario? My hope is that when we see this, it kind of almost looks like, a table where here's my time, here's my hours, and then this is how many cars. So to answer, how would I write the domain and range? List the x values for the domain and y values for the range. And hopefully this is like a blast from the past to what we did at the beginning of the unit where we had tables like this, because when it's discrete, when the data is countable, we list all of the x values for our domain and all of the y values for the range. And that's exactly what we're going to do here with this real-world car wash question. So for my domain, I'm going to start with a little curly bracket, and it's going to be x such that, and now we'll just list 1, 2, 3, 4, and close it. So those are my x values, and now my y values for the range. Here are my y values right here. They are 5, 10, 15, and then the value 20, and that's it. So even in real-world questions, we can have tables or lists of specific points like we did with this question. So it's good to keep in mind that skill definitely comes up in real-world scenarios. That wraps up the car wash question on page 50. So let's move into our next real-world scenario, number 4, on page 51. And this is a really cool question for a couple reasons. One, this is a real model based on data. And if you notice where this comes from, this real-world scenario comes from the Blitzer Intermediate Algebra for College Students textbook. So this is actually a question that a incoming college freshman in an Algebra 1, in a college algebra class, would see. And it's awesome that we have the skills to do it. So let's take a look and see what it says here. It says, the function f of x equals 0.4x squared minus 36x plus 1,000. So just like we do in class, as soon as we see a model that we can highlight, let's highlight it. So I'm going to highlight the model so it stands out. Models the number of accidents f of x. So here it's defined variables. So I am underlining that it's defined the variables per million miles. Oops, get that straight. Driven as a function of the driver's age, x, in years. So x, off to the side, let's write down x equals driver's age And also notice next that it specifies for drivers from ages 16 through 74. So we'll add that to the definition of our variable, ages 16 to 74. Inclusive comes or sounds a lot like the word included. So we're saying inclusive meaning including age 16 and 74. And if we actually look at our graph here, notice it's a solid dot at 16 and 74. And this is the model of that function. So if we were to pull up an online graphing calculator in class or at home and you type this in, you would see this U shape. Notice, though, that past these two solid dots, we have dashes, dash, 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 and a dashed line here, because for the purpose of the real world data, we're just looking from age 16 through to age 74. F of x equals, and I go back and look. Now again, this is a pretty meaty question. A freshman college student in the very beginning of their experience would be looking at this to remember their experience with it in high school. But if we look at our variables, it says number of accidents, so that part we can write down. Number of accidents. But it says more than just accidents, it says per million miles driven. So we're going to add that. Number of accidents per million miles driven. So what that's saying is, like, if there was, I'm just going to make up some random numbers, 20 accidents per 1 million miles. And I guarantee you the number's way higher than that, but that's the idea, is that for every million miles driven, the data says this is how many accidents people have. Let's get into our first question. It says calculate and interpret f of 20. And if anybody's been struggling with function notation, I'm going to add that to the top. F of 20. Identify this information as a point on the graph of f. So we have two things to do. First, we're actually going to use our model, and then we will go look at the graph. So if we go back and read, oh look, I highlighted it so it stands out. So f of 20 means I have a value for x. Wherever we see x, we will plug in 20. So that's going to be f of 20 equals, it says 0.4x squared. So that becomes 0.4, and instead of an x, which I almost wrote by accident, 0.4 parenthesis 20 squared minus 36 times 20 plus 1,000. So I used the equation I highlighted as a model to know what to write. And now we are going to get our calculators out. So if you do not have your calculator, please go get it. I'm going to get mine out. So that we can do this together, because this is where the calculator becomes very helpful. So we are going to type in, see, calculator, take it out. We're going to type in 0.4 parenthesis 20 squared minus 36 parenthesis 20 plus 1,000 and hit enter. And when we do that, we get 440. So I can say f of 20 equals 440. So I calculated the answer, but I haven't actually interpreted the meaning yet. How are we going to do that? Well, we want to go back and look at what we said for our variables. We said x represents the driver's age between 16 and 74 years old. So if it says f of 20, this is a value for x. So we're talking about 20-year-olds. So we can start there. We know that this is talking about 20-year-olds. our output, the y values, represents the number of accidents per million miles driven. So this is 440 million miles driven. So we can write that down. Move this up a little bit. So 440 million that's not how I want to say it. Hold on 1 second. We're saying 440 accidents per million miles for 20-year-olds. Or you could say 20-year-olds, just to give you another option. 20-year-olds got into 440 accidents. Because again, I'm very clear with how I wrote it based on what I read. Number of accidents. So this is the number of accidents. 440 accidents per 1 million miles driven. It's a lot of accidents. But 20-year-olds just got their license, and that happens. But this is real data. So for this time period, people are able to calculate that information. On your own, I'd ask that you press pause for a second and work on calculating and interpreting f of 50 first, and then we'll go back and look at the graph. So f of 50 equals, press pause. I'm going to press pause 2 on my video, and then when you press play, you'll see my answer and we will compare. Hello, I'm back. So, do we match? My answer is 200. I'm hoping that our setup is really good. If you try going kind of piece by piece and something happened, you can show me tomorrow and I'll see what caused us to get different answers. We have our number, but what does that number mean? And we have 2 different options to write a sentence. Well, there's actually more than 2, so if you have another way of saying the same thing, that's great. Go ahead and write your sentence, and as long as it has the same idea as one of these, you should be good. Now, instead of talking about 20-year-olds, what was our input? 50. So we are talking about 50-year-olds. How many accidents do they get in per million miles? I kind of like the sentence right here, this one a little better than this one, so I'm going to follow this top one up here. And so I'm going to say now that based on this math, 50-year-olds got into, however you want to say it, got into 200 accidents per 1 million miles driven. That is really interesting. I mean, if you look, 20-year-olds got into 440 accidents per million miles. 50-year-olds, less than half that number. But you could reason that they've been driving a lot longer, they're a little more mature, they're not as much in a rush, and have more life experience. So you would expect someone who's older or an older segment of the population to get into fewer accidents. The last part that we need to do for both A and B, it says, identify this information as a point on the graph. So just like we have been talking about, our input is X, output is Y. So I'm going to go look for 20, 440, comma 440. That's the ordered pair I'm going to go see if I can find on my graph. So I scroll up. 16 is about here. Well, not about. 16 is here. 45 is here. So 20 is... I'm going to have to kind of guesstimate here. 20 and... or kind of trace that up a bit and then trace across just to see where I'm at. And again, I don't really have anything else here on the scale to help me out. I mean, I know this is 1,000, so I could reason that halfway is 5,000. Excuse me, not 5,000, 500. Now, 20-year-olds got into 440 accidents. This is actually a little high. About halfway. So it is reasonable that this would be correct. 20 and 440 is right there, maybe. I can't really tell for sure because I don't have the scale, but I could reason that's accurate. And let's see if we did our other value was 50-year-olds. So here's 45, 50, maybe right here. Let's see. Maybe we guesstimate it's right there, and now we kind of trace across. And it's reasonable that 220 is right there on my scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. So we are using our powers of reason to place these two ordered pairs correctly at 20, 440 and 50, 220. Great. Let's move on to part C. That question asks, for what value of x does the graph reach its lowest point? So now we are going to go to our graph and look for that point. And I'm looking for the lowest point. Appears to be right here at 45 as an x value. So I'm going to answer that question right here and say 45. The question says, use the equation for f to find the minimum value of y. Describe the practical significance of this minimum value. So the smallest value for y, meaning smallest number of accidents, will take place at that same value, the smallest x value. So let's take that x value and plug it in. F of 45. Once again, I'm going to pause the video right here and I'm going to finish my setup and get my answer, and this time I'm going to write my sentence. So see if you can press pause right now and you do your setup and get your answer and write your own sentence, and then we will come back together when you press play and compare answers. So you press pause and I press pause. And I'm back. So do we match? When I set up f of 45, wherever I saw x, I plugged in 45. And my answer is 190. Hopefully we're like, yay, I got 192. And then my sentence meant that 45-year-olds get into the least or fewest amount of accidents. They get into 190 accidents for every 1 million miles driven. It's our lowest point on the graph, and that's what the point means, based on our labels and understanding of what the variables represent. Our last question says, use the graph to identify two different ages for which drivers have the same number of accidents. Use the equation for f to find the number of accidents for drivers at each of these ages. Let's go look at our graph and see what's going on. So we have to use the graph to identify two different, I'm just rereading the directions before I go look. Drivers have the same number of accidents. All right. So I come over here and I look. If seeing what we wrote is distracting to you, then you can erase it. But let's be a little strategic here. I have these values, 16, 45, and 50. So let me just get rid of this for a second. To avoid having to guess, well, is this 17 or is this 18? Is this 18 or is this 19? If I look here at this quadratic shape, these two values right here look right on the same level. So we're going to check out 16 and 74 and see what happens. Age 16 and age 74. So we're going to do f of 16 and get an answer, and then we're going to do f of 74 and get a second answer and see what happens when we plug those in. So once again, I will press pause, you press pause, plug in 16, get a number, plug in 74, get a number, and then we will compare our answers. These are my answers. Do we match? For both plugging in 16 and 74, I got 526.4. Notice I did hold off on writing the sentence because I'm curious to see what you think the sentence might be, even though I can't ask you because you're watching the video right now and I'm not there to hear your answer. I'm hoping we jotted something down before we talk about the meaning. Once again, these are my ages. So if we were stuck 16 years old and 74 years old. Kind of try to think about what does that mean that they got the same answer. Well, it means that each of these ages, this is the number of accidents. So 16-year-olds, 16-year-olds and 74-year-olds both get into 526.4 accidents per 1 million miles driven. That's it. Interesting data. 16-year-olds just got their license and are definitely expected to, I mean, not expected, hopefully you never get into a car accident, but new drivers are accident prone, and as folks get older, they too sometimes struggle driving at night or not realizing a sign says something. So this is the age when at 16 and at 74, the same number of accidents. Pretty interesting data point. Last but not least, Part E says, oops, sorry about that. Part E says, write the domain and range for the real-world application of this function. So my domain, if I go look at the graph, domain is going to be all about the age, and range is number of accidents. So let's go take a look at the ages. We've touched on it a couple times. My ages run from, if I came in from the left, the dotted line does not count as part of what we're looking at. We're just looking at this solid part of this quadratic parabola shape. From 16 to 74. So I come down and I say 16 to 74. And remember, it said inclusive. So ages 16 is included, it gets a bracket. And age 74 is included, that also gets a bracket. Looking at the number of accidents, I am looking for, let's see, the range. I need to find the smallest y value and the largest to come in from the top. So I'm looking for these two numbers. Now, these follow-up questions came directly from the college textbook, and it is no coincidence some of the math that you are already asked to do. And that happens a lot sometimes, where the question will actually kind of build in answers for the next questions as you go. Let's see what we mean by that. The smallest y value occurs, well, doesn't that sound familiar? The smallest or least amount of accidents. We actually found that out in Part C. We found out that 45-year-olds get in 190 accidents. So 45-year-olds, 190 is right here. That's my smallest y value. And then in this last question, we actually just figured out how many accidents both 16-year-olds and 74-year-olds get into. They both get into 526.4 accidents. So no math needed. We just needed to be able to understand the answers we already found. So just kind of mentally capture those two numbers, 190 and 526.4. 190, comma, 526.4. And we are all done. Great job on these two real-world questions. Quick reminder that we do have a quiz tomorrow. Quiz tomorrow. One more time, quiz tomorrow. On function notation and two real-world questions. One where you are given a domain restriction and you have to find the range, and a second where you are given the range and you need to find the domain. And building your own model, like we've been doing these past couple days, will be part of the assessment. So make sure you're comfortable with identifying M, the rate of change, and B, the initial value, and you'll be good to go. Have a great night, everybody. I look forward to seeing you tomorrow. Bye-bye.